Nurses are asked daily some really difficult questions about the medical field from their patients. One in particular that's really surfaced up recently is how do vaccinations work? What is a vaccination? Given the recent pandemic that was plaguing us in 2020 and is starting to tail off a little bit in 2021, it would be really wise to discuss this, help your patient know and understand this. We're going to go ahead and take this from the view of a virus, though, how the body will respond to a virus. First, we need to understand what is a virus. Well, a virus is neither really living or dead, and the only live-ish thing about it is, well, it's filled with either DNA or RNA. It might have a lipid bilayer or a capsid. It's covered with proteins on the outside, but that's about it for the bugger. So how does it make more if it's not alive? Well, it has to take over other cells. By using its spike proteins, the proteins on the outside, it can interact with markers or other proteins on the cell, their host cell. The marker could be on blood, it could be on neurons, it could even be on defensive cells. The only thing that's really telling us what it does or what it interacts with is if the proteins on the outside of the virus is going to interact with the proteins on the cell. Once it does, the virus can either insert its RNA and then, or if it has DNA, it can get absorbed and insert its DNA into the DNA host. They then will multiply those cells using cell machinery, and when they're ready, they're usually just going to pop the host cell to release themselves. So how do we fight against it? Well, if the virus is outside the cell, we could have a macrophage come and dissolve it. We could have complement come along. It could attach to it, causing several things to occur. Such that the virus will no longer be able to attach to the host cell. No touchy, you may not touch. We'd also just punch a hole in that virus and induce inflammation. It can also induce that inflammation, which also attracts and facilitates macrophages to come along and take a bite. If the virus is inside a cell, well, the cell could release interferon, which basically what it does, it stops itself from making new stuff inside itself. No more self-proteins, and no more proteins itself means no more viruses also. It can also, this interferon, attract defense cells, natural killer cells, which will end the cell. The cell could also present a piece of that virus, which can activate other cells, such as the cytotoxic T cell, which will trigger lots of things, like attracting macrophages, because they're going to be needed to help clean up what's about to happen. The cytotoxic T cells and natural killer cells will trigger self-destruction of the infected cell, releasing its contents. We've seen macrophages several times now, so we probably should discuss what these things do. They do a lot of things. They can, well, induce a fever, induce inflammation, and, well, induce T helper cells. And T helper cells are the major coordinators and stimulators of the immune system. Activating them is the major way to start up the adaptive immunity process, which includes activating T cytotoxic cells and B cells. All these cells can adapt specifically to a part of the virus, aka an antigen, and hunt it down. That's why it is adaptive. All adaptive cells undergo mitosis when activated, which is important because you need some of them to hang back and become memory cells just in case of an infection. The other portion goes into active duty, actively fighting the infection. So cytotoxic T cells, which is an adaptive immunity cell, we've talked about, just adding that they hunt a very specific part of the pathogen. B cells, which we haven't talked about yet, become plasma cells and make antibodies. These antibodies attach to antigens on the virus and excite the immune system. They go, ooh, yummy. After infection, the memory cells will stick around in the lymphatic tissue, such as the lymph nodes. This is to help fight the next infection a lot quicker. So there is a little famous graph. This one comes from John Wiley and Sons back in 2017. But we're going to go ahead and take a look-see at this. This is the x-axis, refers to passing of days. The y-axis, this vertical line, talks about how much antibodies are out. In units, it doesn't give milliliters or grams or what have you. You're going to notice that we have an IgM and an IgG. Ig, it just means immunoglobulin or an antibody. M. IgMs are just created by immature B cells that are not very super specific. They're floating around looking for things to see if they can bind with them. IgG is the specific one. You're going to notice at the very beginning, at day 0, you get infected. An IgM comes along and notices something's wrong, and these immature B cells start going, okay, we need to fix this. But several days later, like 5, 6, 7 days, you're seeing that these IgG, these ones that are very specific, come along to try and help fight. And they never truly drop off down below a specific number after the infection. You can then get exposed to the same pathogen, and notice what happens. First, IgM bumps up really quick like normal, it used to last time, but IgG does, which is really specific to the antigen and can fight it really quick and help the immune system fight it off. So if I were to summarize the chart, it's like this. The first responses are almost like, hello, fellow cell. Hey, wait a minute. Oh, too late. The second response in that chart would be like, hello, my fellow. Oh, my word. And dying. Most of the time, knocking it out. What happens is the virus goes away, or whatever happens just goes away and gets destroyed before it even has a chance to cause signs and symptoms, or even spread sometimes. So the question is, how do we get our bodies to respond in this fashion? Like, the second question is, why even bother? Let's talk about the second question first. During the first infection, lots of bad things go on. Take COVID-19, for example. It likes several cell types, like lungs, muscles, and tissues, oh boy, which will then pop these cells and possibly leave scar tissue in its place. Not great if you want a good lung capacity, decent neurological control, and well-responsive muscles. The body's innate immune response also makes things not so pleasant for us. They produce multiple signals, cytokines, that cause inflammation, heavy mucus production, fever, pneumonia, and confusion in COVID patients. The aftermath of COVID can also cause scar tissue in lungs, brain, muscles, and heart. It's not good to have those type of scar tissues there. Long-lasting or permanent oxygen dependence, continued mind haziness, chance of stroke and seizures increase, as well as there's an increase in the risk of developing other neural issues such as Parkinson's, Alzheimer's, and Guillain-Barré syndrome. So again, I ask, how do we skip over all this bad stuff? How do we get this stuff not to happen? Well, we got to train that immune system to fight off that virus. But we do it without the virus. We can do this to train the body to fight the virus without the virus in several ways. But to be brief and just to give one example, probably the most widely used, is just to give a part of this virus to learn from. So like, for instance, the spike proteins. Spike proteins is usually the easiest one to create. You stick the spike protein into muscle or under the skin, and then it just causes the immune system cells to react and begin setting off cytokines, which means that you're going to feel a little bit of muscle soreness from the inflammation, and because you're hanging out with macrophages and all that stuff, you're going to induce a fever. I wanted to point out that, but again, this is whole immune cell stuff, the fever, the soreness, it's just part of the immune cell's job. That's what they do. This thing, this little spike protein, doesn't do that. It doesn't directly do that. The virus isn't active. It's not there to replicate and do damage. It's just, this little thing is just to help us learn. And that explains why some people feel sick after getting a vaccination. With that, that is the end of our discussion and our overview of the immune system and explanation of the vaccination and how it works and what's so great about it. Thank you and good luck.